In this video, we're going to learn how to solve constant coefficient differential equations. So what is a constant coefficient differential equation? Well, if I look at this one, y double prime minus y prime minus 6y is equal to 0, the coefficient of the dependent variable y and its derivatives are all just numbers. 1 out the very front, even though it's not written down, minus 1 in front of the y prime, and minus 6 in front of the y. So it's not just a linear differential equation, it's a constant coefficient one. The coefficients are not even allowed to be functions of x, they have to be actually constants. And this is a second order constant coefficient differential equation because the highest derivative is 2. Indeed, this is our first example of an order 2 differential equation. All our previous examples were order 1. So what's our methodology? Now it's kind of interesting. We're going to make a guess. I'm going to guess what the answer to this is. I'm going to guess that it's of the form e to the rt, where r is some number that I don't know. Now, it's at this point not at all obvious why we should guess e to the rt, but let's just suppose that that is the solution and see what happens. So I'm going to do that. I'm going to plug in this solution everywhere. So 2 derivatives of e to the rt gives me r squared e to the rt. Then it's a minus r times e to the rt when you take one derivative. And finally, minus 6 e to the rt equal to 0. So that's me just substituting this guess into this differential equation. And by the way, in differential equations, it's totally okay to guess. This is kind of like with integration. If you can guess an antiderivative and it works out, power to you. Now, I do notice that there's an e to the rt everywhere. So why don't I cancel those? E to the rt is positive, so I can do it. And that just leaves me something that's called the characteristic equation. So this is a polynomial. R squared minus r minus 6 equal to 0. That's a polynomial in the variable r, the thing we introduce when we guess e to the rt. So if there is a solution of this form, it must be the case that the r solves this particular quadratic equation. I can solve that quadratic equation. I can factor it easily, r minus 3, r plus 2. And that gives me 2 different solutions to the r, an r1, which was 3, and an r2, which is minus 2. So I've made my guess of e to the rt, and I've decided that the only way the r could work out is if it was one of these two answers. Okay, so if I just look at those pieces, here is my general solution to this second order constant coefficient differential equation. I know it's a mouthful. It's, well, the possible ways that I could add up exponentials of this form. An e to the 3t, that was our first root. An e to the minus 2t, that was our second root. And then coefficients of c1 and c2. And it turns out that's it. That's all I need. Indeed, as we saw in the previous video when we just talked big picture about the theory of second order differential equations, we said that what we needed to find to get a general solution was 2 different linearly independent solutions. And e to the 3t and e to the minus 2t are linearly independent. They're certainly not a multiple of each other. So these are 2 different solutions. They're linearly independent, and thus the general solution by our theory has to be written in this way. A linear combination of these 2 solutions, c1 e to the first root times t, and c2 e to the second root times t. Okay, so that's the solution to this differential equation, but what would happen if I also had an initial condition? But I actually have a c1 and a c2, 2 different constants. And so I need to have 2 different initial conditions. So I'm going to specify, I'm just making these numbers up, that y of 0 is 1, and that y prime of 0 is equal to 2. I'm going to have 2 different initial conditions to find the 2 different constants to my 2 different solutions to my second order differential equations. It always works like that. So how can I deal with this? Well, one initial condition is in terms of y, and the other is in terms of y prime. It's a y prime of 0. So let me go ahead and take the derivative of this to get my y prime as well. Just taking the derivative, e to the 3t becomes 3 e to the 3t, and so forth. Now let me substitute in my 2 differential equations. For the first one, y of 0 is equal to 1. Basically, for y, I plug in 1, and everywhere there's a t, I plug in 0. As e to the 0 is just 1, this is just going to become c1 plus c2. So that's my first initial condition plugged in. Let's do the second. Okay, so now I had to plug this into the derivative. So y prime is going to be 2. I plug in 0 again, and then the exponentials are going to be going to just 1. And so I get c1 times 3 minus c2 times 2. So this is what happens when I take my 2 different initial conditions and plug them into my solution and to the derivative of my solution. Let's get rid of a bunch of the extra fluff here. And what I just have is 2 equations, 2 unknowns. I can solve this. This is a linear system of equations. Maybe I'll look at the first one first, the 1 equal to C1 plus C2, and I can solve that, saying C1 is 1 minus C2. Then if I take 1 minus C2 and plug it into the second equation, you're going to get, well, 1 minus C2 times 3, and then minus C2 times 2. I can rearrange this, clean it all up. It's 3 minus 5C2. And now if I look at this equation, 2 minus 3 is minus 1. Minus 1 equal to minus 5C2. C2 has to equal to 1/5. And as soon as I know what the C2 is, I can look back at my previous equation that C1 was 1 minus C2, and thus my C1 is 4/5. So I've now solved my two constants. In my general solution, it was a C1 e to the 3t and a C2 e to the minus 2t. But I now know what the C1 and the C2 is. I can just plug them in, and so my final answer to this initial value problem is 4/5 e to the 3t and 1/5 e to the minus 2t. Now, this was all great as a first example. However, there's multiple different types of cases that can come up when you solve a second order constant coefficient differential equation. So in the next video, we're going to dive a little bit more into the general methodology, the general theory of how to solve all the different second order constant coefficient differential equations just like this one.